there's a single thread connecting the silk brocades of 18th century Lyon to the smartphone in your pocket. It runs through Napoleon's France, across the Atlantic to Census Bureau offices, and into the digital architecture of the modern world. This is the story of that thread, and of how a simple weaving machine became the mechanical ancestor of the computer. Part 1. Threads. The discovery of silk, legend has it, occurred more than 4,000 years ago, when a cocoon fell into the teacup of a Chinese empress. To her amazement, she found she could unwind a single, unbroken thread from the cocoon. The shimmering strand could stretch up to a kilometer, creating a fabric that was remarkably soft, durable, and resistant to dirt. And for centuries, the Chinese fiercely guarded the techniques of silk production. The secret finally reached Europe in 550 AD, when two Persian monks smuggled silkworm eggs to Constantinople, in modern-day Turkey, for the Byzantine Emperor Justinian, giving rise to the European silk industry. But silk was just thread. To transform it into fabric required weaving, a technique far older than this precious material that interlaces two sets of threads at right angles. Early weaving used a hand loom, a simple frame that held parallel threads tight and separated. The weaver would then pass a shuttle, carrying another horizontal thread back and forth through these vertical threads, going over one, under the next, over, under, building up the fabric one row at a time. Though effective for creating plain fabric, this loom was incapable of producing complex patterns or decorative images. Creating patterned fabrics required revolutionary control, the ability to raise some warp threads while lowering others. This determined which colored threads would show on the fabric's surface and which would hide beneath, allowing weavers to build up intricate designs thread by thread. The draw loom, which emerged in China around the 2nd century BC, was the first loom capable of this pattern weaving. However, this innovation came at a considerable cost in efficiency. The draw loom required two operators, a master weaver and a draw boy, who manually raised cords for each row to form the design. Even skilled teams could weave only a few rows per minute. A single inch of brocade, a richly patterned silk fabric, could take an entire day. By the Renaissance, the French city of Lyon had become the silk weaving capital of the world thanks to royal patronage and its proximity to Italy's master weavers. The wealthy aristocracy's insatiable appetite for ornate silks created enormous demand, but the industry remained shackled by the draw loom's limitations. High prices and restricted production were inevitable consequences. In an age that would be defined by rationalism and industrial ambition, inventors soon turned their attention to mechanical solutions. In 1725, Basile Bouchon used a continuous band of perforated paper to control which warp threads were to be lifted, although the weaver still had to manually raise the selected hooks each time. Basile Bouchon was the son of an organ maker and adapted this idea of using perforations to control individual threads from the barrel organ, a hand-cranked automatic instrument like the ones his father built. The punched holes allowed air to pass through to play specific notes, just as the tapes moved needles to select individual threads. Paper tapes were soon replaced by linked cards that could be changed to create different patterns. And the next breakthrough came from Jacques de Vaucanson, building a mechanism that finally eliminated the draw boy, selecting threads and raising them automatically. Yet none of these clever mechanisms achieved widespread adoption. What the silk industry needed was not just ingenuity, but practicality, a system robust enough for daily use in the workshops of Lyon. The man who would finally solve this problem was born into the world of silk weaving, but his path to invention would be anything but straightforward. Part 2. Joseph Marie Jacquard. Jacquard was born in Lyon in 1752, the son of a prosperous master weaver in a city that lived and breathed silk. Like many artisans' sons, he received no formal schooling as his labor was required in the workshop. When his father died, 20-year-old Joseph inherited the family workshop, a vineyard, and quarries. But with little aptitude for finance, he slid into a precarious existence. By 1783, married and with a young son, Jacquard was financially ruined. It was the chaos of the French Revolution that pulled him from obscurity, though it nearly cost him his life. During the brutal siege of Lyon in 1793, the city rebelled against the revolutionary government. Jacquard and his teenage son fought in the defense of their city on the side of those who provided luxury goods to the aristocracy. When Lyon fell, the two fled to avoid the guillotine, reinventing themselves by joining the opposing army of revolutionaries under false names. They marched to the Rhine, but the military adventure ended in heartbreak. In 1797, his son, Jean-Marie, was killed in battle. Grieving and wounded, Jacquard returned to Lyon in 1798. He drifted through odd jobs until the political winds shifted once again. The rise of Napoleon Bonaparte brought a new emphasis on rationality and industrial modernization. It was in this environment that Jacquard finally focused his mechanical talents on a problem that had plagued his city for centuries: the inefficiency of the draw loom. Jacquard's genius lay in his ability to perceive the limitations of the existing technology and integrate different solutions into an automatic system. He knew that the existing draw loom was merely a manual aid, like an abacus, not a true machine. Jacquard's first breakthrough was a foot-treadle-operated loom. This machine, a minor improvement over manual methods, used foot controls to mechanically manage a limited number of warp threads. It produced simple, repetitive patterns, like stripes or small florals. Unlike his later invention, its pattern options were fixed and could not be quickly reprogrammed. Building on this success, Jacquard entered a national competition for an improved fishing net loom and won. This victory brought him financial security and, crucially, connections to influential figures in French science and government. By 1804, Jacquard had finally perfected his ultimate goal: the loom capable of handling the most complex designs. The key was a chain of punched cards made from stiff pasteboard. Each card represented a single row of the pattern. The holes punched into each card were instructions, a kind of early software that told the loom exactly what to weave. The mechanism worked on elegant simplicity. As each card moved into position, it pressed against a grid of thin metal rods called needles. Where there was a hole, a needle passed through and lifted a specific thread. Where the card was solid, the needle stopped, leaving that thread down. Hole by hole, row by row, the pattern emerged automatically. The impact was staggering. Before Jacquard, two skilled workers laboring together could manage perhaps 2 rows of fabric per minute. A single operator with a Jacquard loom could produce up to 48 rows in the same time, a 24-fold increase in speed. The draw boy, whose exhausting work had been essential for centuries, was suddenly obsolete. Lyon's silk workshops could finally meet the insatiable demand for their intricate brocades. The city secured its position as the world's silk capital. But Jacquard had achieved something deeper than efficiency. By separating the machine from its instructions, hardware from software, he had introduced the concept of programmability itself. To weave a new design, you simply swapped in a different chain of cards. The loom remained the same, only the program changed. This was the critical insight that would echo through the centuries. The Jacquard loom wasn't just the most complex machine of its era, it was the mechanical ancestor of the computer. The invention caught the eye of Emperor Napoleon. Desperate to outpace British industry, Napoleon visited Lyon in 1805. He declared the Jacquard loom public property, but compensated the inventor generously with a pension of 3,000 francs and a royalty on every machine installed. Napoleon was reportedly delighted by Jacquard's modesty, contrasting him with the swarms of courtiers begging for favors. The loom faced early resistance from threatened draw boys, who, according to local lore, once threw Jacquard into the river. Yet the invention quickly spread. By 1812, over 10,000 Jacquard looms were in use in France. Jacquard was honored with a gold medal and the Cross of the Legion of Honor in 1819. He eventually retired to the village of Oulin, where he lived out his days in comfort, tending to his garden and receiving distinguished visitors. He died in 1834 at the age of 82. His legacy, however, extended far beyond the silk trade. In 1838, a portrait of Jacquard was woven in silk using his own invention. It required 24,000 punched cards to create an image so fine it looked like an engraving. A copy of this portrait found its way into the hands of Charles Babbage, an English mathematician pursuing an audacious dream, a machine that could perform any calculation imaginable. Part 3. Weaving information. The Jacquard loom was more than a machine. It was a concept waiting to be reimagined. Its punched cards held a secret that would transcend the world of silk and lay the foundation for the digital age. The first to grasp this profound connection was Charles Babbage. Frustrated by the constant errors he found in man-made mathematical tables, the essential tools for navigation, astronomy, and engineering, Babbage dreamed of a machine that could calculate with perfect accuracy. Babbage had an epiphany. If a sequence of cards with holes could command a loom to weave a complex portrait, then a similar sequence could command a machine of gears and levers to perform a complex calculation. The Jacquard loom's binary system, hole or no hole, thread up or thread down, was the key. Babbage adapted this principle for his ambitious analytical engine, the first ever designed for a general-purpose computer. It had a mill to perform calculations and a store to hold numbers, all controlled by punched cards. Working alongside him was Ada Lovelace, the mathematically gifted daughter of the poet Lord Byron. More than a mere assistant, she was a visionary interpreter of Babbage's work. She, too, saw the true potential of the analytical engine, famously writing that it weaves algebraical patterns just as the Jacquard loom weaves flowers and leaves. Lovelace understood that the machine could manipulate not just numbers, but any symbol, prefiguring modern computing. However, Babbage's dream was a century ahead of its time. The precision engineering required to manufacture thousands of identical gears was too costly and difficult for the era, and his analytical engine was never fully built. The idea of the programmable machine lay dormant, waiting for a new, practical problem to solve. That problem arrived across the Atlantic. By the late 19th century, the United States was facing an information crisis. The population was exploding, and the manual method of counting the national census had become unworkable. The 1880 census took nearly a decade to process, and officials feared the 1890 census would be obsolete before it was even finished. A young engineer named Herman Hollerith stepped forward with a solution. Critically, he was familiar with the Jacquard loom through his brother-in-law, a silk weaver. Inspired by the machine's ability to store information on cards, Hollerith devised an electromechanical system. Each person's census data, age, sex, origin, was punched onto a single stiff card. These cards were then fed into a machine where a set of pins pressed against them. Instead of lifting threads, Hollerith used the Jacquard principle to make an electrical connection. When a pin passed through a hole, it dipped into a cup of mercury, closing a circuit and advancing a mechanical counter on a large dial. This was the Jacquard loom, reborn and electrified. Hollerith's tabulating machine was a triumph. It processed the 1890 census in a fraction of the time and cost, saving the government millions of dollars. The machine didn't just count, it sorted and cross-referenced data, providing insights into the American population that were previously unimaginable. Hollerith founded the Tabulating Machine Company in 1896 to commercialize his invention. The business thrived on government contracts, but Hollerith, more an inventor than a businessman, struggled to see its wider potential. That task fell to others. In 1911, the financier Charles Ramlake Flint, a master of mergers, purchased Hollerith's company and combined it with several others that made time clocks and industrial scales. The new entity was called the Computing Tabulating Recording Company, or CTR. A few years later, a dynamic and ambitious salesman named Thomas J. Watson was brought in to run the company. Watson was not an engineer, but he was a visionary who saw that the business of the future was the business of information. He understood that Hollerith's machines, the direct descendants of Jacquard's loom, could do more than just count people. They could revolutionize accounting, inventory, and every facet of modern commerce. Under Watson's leadership, CTR transformed into a powerhouse. The punched card machines, still operating on Jacquard's binary principle of holes and blanks, spread into businesses across America and beyond. By the early 1920s, Watson's company was no longer just tabulating census data, it was transforming how modern enterprise functioned. In 1924, Watson decided the company needed a name that matched his ambitions. He wanted something that spoke not to tabulating or recording, but to the global transformation he envisioned. The thread that began with a Chinese empress and ran through a French weaver's workshop now culminated in a new name, one that would define the computer age, the International Business Machines Corporation, better known as IBM. Epilogue. The history of a successful invention is like the story of a river as it flows from its source to the ocean. The journey from the wooden looms of Lyon to the global reach of IBM illustrates the powerful and often unpredictable evolution of technology. Jacquard's invention was the modest source of a river that gathered momentum and volume over 2 centuries, eventually meeting the ocean of the modern world. The first stretch of the river was driven by pure mechanical ingenuity, with Joseph Marie Jacquard himself providing the essential concept of programmability. This stream was taken up by Charles Babbage, who used it to dream of the analytical engine. The river met its next great tributary in the United States, where necessity drove innovation. This was the practical working loom that wove information, finally realizing the commercial viability of the punched card. The river's course was then accelerated by the ambitious spirit of Thomas J. Watson, who guided Hollerith's invention into the mainstream of commerce. By the mid-20th century, the river split into a powerful delta of electronic invention. World War II and the need for high-speed calculation spurred the invention of the vacuum tube and the first all-electronic computers like ENIAC. Yet even in these gargantuan electronic brains, the punched card remained the standard interface for decades. Today, the physical punched card is long obsolete, replaced by microscopic silicon chips and magnetic storage. But the core logic, the architecture of separability, the digital concept of on-off logic, is precisely the legacy of Jacquard's loom. The river has reached the ocean, manifesting as a dense global network of interconnected digital devices. It is fitting that the greatest of these networks is called the World Wide Web. This metaphorical web, with its infinite connections and boundless information, is the ultimate fulfillment of Jacquard's original ambition, a flexible, universal system capable of realizing any pattern the human mind can conceive. The story is a testament to the fact that the greatest technological revolutions are often woven from the most ancient of threads. This was Jacquard's Web by James Essinger, first published in 2004. Thank you for listening.